Lockdown. Okay, I'm recording. So we understood that there's a natural object entering in the discussion of diffusion, that is this magic effective potential. And we understood that there is a relationship between the effective potential and the relaxation timescales, or if you want, the kinetics in general. By kinetics, I mean anything that has to do with time. In particular, the spectrum of the effective Hamiltonian is the same as the spectrum of the Fokker-Planck equation, because remember, we are dealing with a very special non-unitary Fokker-Planck operator that has real eigenvalues, positive definite eigenvalues, and has a nice relationship between left eigenstates and right eigenstates, or if you want, the right eigenstates of the adjoint operator. And what we were discussing is that a spectrum of these two operators has to do with relaxation scales. So the relaxation scales are quite fundamental object in the statistical mechanics of complex systems. And in particular, we have discussed the fact that there are situations in which the spectrum of relaxation scales is gapped, has some non-trivial structure. And this is typically when there's a hierarchy oh, I guess hierarchy goes with a one I. Hierarchy of barriers, and therefore a rugged energy landscape. Now, you can make all sorts of descriptions here. You might describe, the spectrum basically is a truth teller, tells you quite a lot. For instance, if you have a glassy state, you remember a glass is a state with an exponentially large number of nearly degenerate classical minima, right? Now, a glassy state has an exponential number of nearly degenerate states near the Boltzmann distribution. So, and in order, from start point on, basically, after you basically. Come adesso?
Adesso sì.
Ora sì.
Okay, so were you with me with the glass?
Yes.
I was then saying that there are systems for which the relaxation timescales are not determined by rate limiting processes that are energy barrier, but they might well be entropy barrier. For instance, think about a gas in a box with a tiny little hole in the wall, very tiny, and then you have your gas here. There's no energy barrier here because the system can flow through. But you have a very limited, your system has to go through a very small hole in order to go through. And there's only very few configuration of the gas through which this can happen compared to all the others in which it doesn't happen. That's a typical example. There are better examples of entropy-driven process. Typically, I would say an entropy-driven process is a process that, so in complex system, you might encounter situations in which you're dominated by entropy. Let me give you the most radical example I know, the golf court. You have a reasonably flat green with a hole. And maybe, the system might even have a slight bending towards the hole. However, there are so many configurations around, then if you have a particle diffusion here in a large grain, you will never basically find the hole. It's very difficult for the particle to find the hole. So this is an example where you need entropy reduction to perform a rare transition. And we'll dig a little bit better on that later on in the course. Today we're going to do something slightly simpler. But let me just say that proteins, for instance, I used it quite often as a prototype of a complex process. They are produced with a chain, like a open chain. And when they are in this so-called unfolded state, then clearly their entropy is huge. How many equivalent configuration has an open string? Energetically equivalent configuration has an open string. Basically huge, right? They reach a point where they have only one configuration. I'm drawing this like this because it basically, like, every single amino acids in the protein is locked into a specific combination, because that's where the protein becomes biologically functional. But this is where biology takes place. So it has to be in a specific shape. Clearly, entropy is hugely reduced. Now, there's also energy gain, because anytime you get two amino acids together, you form a bond, and you get the gain delta U. However, at the beginning, these bonds come at a huge entropy cost. You can't hear me anymore? Okay.
We can.
No, I see somebody doing this. I thought. So forming bonds comes at a huge entropy cost. So at the beginning, the quantity of interest in a thermal environment, in fact, the state function of a thermal environment is the Helmholtz free energy, not the energy, right? And the Helmholtz free energy is the energy minus the temperature times the entropy. So what happens at the beginning, you're forming, maybe you're gaining, I don't know, a contact between two amino acids can be worth 2 kT. But the entropy reduction might be much more than that in units of kT, in units of K, multiplied by T. And so at the beginning, during the reaction, entropy grows. Entropy decreases faster than the energy decreases. And therefore, you create a barrier. But you see, there are many energetically favored states that the protein can go. But finding them by just diffusion is very difficult. And most of the time, the ones you find are not the correct ones. So you have to wait for a right fluctuation that breaks it. However, once you have formed a sufficiently large number of entropy, maybe you have formed all of this and the beginning of this, if this is a two, like if the final state is like a double hairpin. Now, this poor chain here cannot go very far, right? So the entropy reduction in forming the very few last bonds is small. But now energy remains the same and gains. So that's why eventually you go down, you get a more stable state. So I will go back on these notions later on, but it's important for you to understand that While from the point of view of stochastic dynamics, we are always concerned microstates X in configuration space. And of course, anytime you have an object that depends on a configuration, any concept like entropy makes no meaning, right? Because entropy concerns ensembles of configurations. However, in the end, there might be the probability of performing a transition, knows eventually through the path integral that, the path integral might receive contribution only from those paths who go through the hole, and they have a very small, they are a very small fraction relative to those who don't go through the hole. So the measure of the accessible path are very small. Going back to this example, right? I have a particle, an xi, xf. Now, in principle, if I didn't have this limitation, all the paths that go from here to here would work. There would be many. And they would have a relatively low action because the smallest action is a straight line in diffusion. However, if I have a hole, first of all, the action is longer, so the probability is proportional to the inverse of the action goes down. So you see fewer events in which you see the particle on the other side. And not only that, if my hole is very narrow, there is very few paths. So, if I do this integral, I have a very few paths around the most probable one that will contribute. So I think it's time to build an analogy with classical mechanics. Remember, when we were doing classical limit, we were taking the action, imposing stationary variation with respect to the path, and this would generate the classical Newton's equation of motion, right? And the interpretation of this is that I have 2 points. I have in principle all possible non-differentiable paths between these 2 points. However, most of them interfere destructively, except very, in principle, in certain limit, a short bundle of paths around the classical ones. I'm drawing the classical in red and the bundle of paths that constructively interfere in yellow. These are quantum fluctuations around the classical path. So in the limit in which the action is large in units of h bar, all you see is the classical path. Now, we can do exactly the same thing in the case of stochastic path integral. But now this is the Onsager-Mach loop action. And ask yourself, what are the dominant paths? What are the most probable paths? What happens in the large action limit? So remember, the action is a dimensionless object, of course, if you write it this way. You can, but depends how you write it. A way to write it is this: d over kt, remember, squared. And remember, d is kt over m gamma, so you can write this as m gamma over kt. So you're welcome to pull out a factor beta here and forget about this kt here, and I get only m gamma. And then I have the integral d tau x dot plus grad u d over kt squared. So in the low temperature limit, when beta goes to infinity, I'm in the equivalent of the classical limit, like actually, to be quite precise, since I have this factor that comes out and there's 1/4 here, since I have this m gamma that I can pull out, let me pull beta m gamma going to infinity and pull it all out from here, because this will tell me and then an action will contain only 1/4, because this will tell me that indeed this is a scale that contains both temperature and diffusion, and in fact it's basically the diffusion coefficient. So in the limit of low diffusion, which is 1/d going to infinity, there's only one path. And I can immediately give you an example. You remember Brownian motion, right? Very good. Now, rather than looking at the fine grains of powder, drop any, I don't know how to say that in English, actually. It's one of the few words I don't quite remember. Un bullone, o uno spillo, o la pallina, o un piombino da pesca. If you drop it, all you see is one trajectory. The little guy going down to the floor, right? Why? Because the diffusion coefficient of that object is very small. Right? It's so small that there's basically no diffusion. And if there's no diffusion, you have one trajectory. Now, so what are the equations that these guys obey? Well, if you write this in terms of the famous effective action, of course, you remember the effective action was like integral d tau x dot square over 4d plus v effective, remember? I like this expression because it's very simple to work out. The equation of motion is a Newton equation with an inverted potential. So the equation of motion is actually 2d x double dot equals now plus the gradient of v rather than the minus, because this is not the action, is the action in an inverted potential. And this equation gives rise to what we define. Actually, we did all this theory in my lab, and this is called the dominant reaction pathway equation. If you Google dominant reaction pathway, you find all the literature we wrote about this. And we applied it to simulate protein folding. So the dominant reaction pathways obey a Newton equation. And those are the equivalent of the classical trajectories. And I will not give you all the story about this. Let me just say that I'm quite excited that maybe I'll tell this at the end of the course, but we have just figured out and published on Physical Review Letters a way of computing the dominant reaction pathway using quantum computers, which is kind of an exciting development because it paves the way for the future development of quantum computers to be applicable to biology. So if anybody of you would be interested in a thesis at the frontier of, say, quantum computing and biological sciences and biophysics and statistical mechanics, that's a field where we have a lot of work to do, that we basically started on. Okay, moving forward. In the second part of this lecture, I'd like to have you work for a while. And I would like to compute, finally, something with you. So we take a potential. This is a physical potential. We take one particle in 1D, and we put in, guess what, in an harmonic oscillator. Rather than putting here the frequency of the harmonic oscillator, let me just take the second derivative of the harmonic oscillator, and I call it K. So it's a simple harmonic oscillator. Nothing particular. Okay? And now we suppose we have a particle with diffusion coefficient D, obey an overdamped Langevin equation. And now we are asking, what is the relaxation time for this system? Okay, so I would like you to formulate this problem, and let me give you a hint. Use the analogy with the Schrodinger equation. Okay? So I'd like you to think about this for yourself for, say, 5 to 10 minutes. And if you're stuck, then we discuss how to move on. Okay? Is anybody stuck at the starting line? We all got the idea where to start. So the way I would start is I would work out the effective Hamiltonian and then try to diagonalize it, okay? And then from there, the lowest eigenstates besides the ground state, which is expected to be 0 if I'm doing things correctly, because this is the Boltzmann, the lowest eigenstate is expected to be the slowest relaxation scale, right? Okay, so do we all agree? Do we all agree on this? This is the force squared, and this is the Laplacian. Now, of course, one way to do that is to, now you can solve the problem because you know there's a so to say standard way to solve it, which is probably the one that you have followed, and it's certainly the one that I followed at the beginning, which consists on saying, okay, I can map this problem into an effective quantum problem in which let me call 1 omega m effective omega square effective to be precisely d over 4 kt square k square, right? Because this is a constant. So the gap between the ground state and the energy spectrum and the first excited state must be something like this, right? So you can build your mapping, and then basically from the fact that you know the spectrum of an harmonic oscillator, then you can get the first excited states and any states, okay? However, I want to suggest a slightly faster way of doing this, and I want to do that because it tells us something. Now let's go back to this potential. Now, as you see, this potential contains a constant. Now, in quantum mechanics, the physics is unchanged if I add to the Hamiltonian an overall constant. You all agree, right? And the reason is that basically, if I have my evolution, let me do it this way, and I add a constant to the Hamiltonian, and in particular to the potential, which is part of the Hamiltonian, then clearly all I'm doing is adding a phase to my propagator. And as we know, phases are not observable, because when you take the square modulus, they disappear. Overall phases. Of course, relative phases, that is difference between energies, they of course are observable. But this is not really quantum mechanics, and there is not really phase here. In particular, we know that the Boltzmann solution P naught equals 1 over z e to the negative beta 1/2 kx squared must be a solution of the Fokker-Planck equation and of the Schrödinger equation. And from here you can get a solution of the Schrödinger equation, right? So in particular, this should be 1/2 e to the negative b half 1/2 k x squared psi naught, where psi naught is this is my psi naught. So I've just split this into terms. This is my psi naught. This is again psi naught, but this is just a prefactor minus beta half times u. And I know that psi naught must be, I know from what we said in the previous lecture that this must be true. And this is essential, otherwise I don't have thermal equilibrium. We discussed that, right? But now I remind you something you'll certainly remember, that if I'm in a harmonic oscillator, I have something called 0-point fluctuation. or 0-point energy, actually, which graphically is represented by the fact that the ground state of the harmonic oscillator has an energy 1/2 h bar omega, while all the energy is relative to the classical ground state. And if you remember your quantum mechanics, the origin of that is that a wave function has a finite curvature, therefore it has kinetic energy because it's confined, and therefore its energy cannot be zero. It explores regions of finite energy potential, and it has finite kinetic energy. As a matter of fact, it has 50% kinetic energy and 50% potential energy. So now, but now I know that this term here so if I close my eyes to this for a moment, I would have exactly the problem that I discussed with this spectrum with a 0-point energy, right? And then I have a constant. But as a result, I know that the ground state of this system has what energy?
Zero.
Zero. Therefore, I have all the ingredients to compute 1/2 h bar omega, right? My 1/2 of h bar omega is equal to this times this. Because this is canceling exactly the 0-point fluctuation to make sure that I get zero. And if you do all the calculations, discover that that's correct, of course. Okay? But that's a shortcut you can put. So if I do that, I can write d over 4k t squared and then I have this 2 kbtk where k is the second derivative in the origin of the potential. Okay? And therefore, I know that the energy between the first the lambda 1 minus lambda 2, lambda 0, which is basically lambda 1, is the energy between the first excited state and the second, from ground state and the first excited state. That's 2 1/2 of h bar omega, right? So this must be twice this number. Therefore, it is equal to d over kt times k. And already from here, I'm copying this again. Already from here, we discovered something interesting, because if you use the fluctuation dissipation theorem, let me remind you that the diffusion coefficient can be written in the following form. So we get this result, which is actually quite useful. The relaxation rate does not depend on temperature. So what does that mean? It means that I have my system here. First of all, the relaxation rate does not depend on where I start in first approximation. Well, no matter which point I choose, I put my system, as long as I put all my particles in the same configurations, say I put a delta function here, 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 I relax basically in the same time scales. And that makes sense because it's a stochastic process. Basically, they all drive down until they build up the Boltzmann distribution. If I have a very slow diffusion process, so if this viscosity is very large, then the relaxation rate is very small, and therefore the relaxation time goes to infinity. If I have a heavy particle, it will never thermalize. I think it's also quite interesting to understand the numerator. The numerator is telling me that the steeper is the well, the faster is the relaxation rate. Can anybody see why? Physically, I want to have I want to stimulate your physical intuition here. Don't discuss mathematics. First, give me your intuition. Why is that if I have a very narrow slater? Then
because there is a bigger force that brings you to the minimum.
yeah, but you see, you're right, but the Boltzmann distribution is not a particle in the minimum. The Boltzmann distribution is actually a distribution. So I would understand if you converge rapidly here, but then you have to move from here to build a distribution. You have to go against the force. So you might argue on the opposite direction is once you get very fast to the bottom, but how do you move from the bottom, right? So why do you think it takes little to thermalize? So what is thermalization? When do you reach? What is one of the most important assumptions you need to make in order to discover Gibbs' theory of the ensembles? Let's list the assumptions you make. Anybody?
Ergodicity.
Ergodicity. Ergodicity. What does ergodicity mean?
That you explore all the phase space.
All the phase space that is really available. Now, this concept of available phase space, as a student, was mysterious to me. And this is one of the examples that makes it clear. That's why I wanted to insist on that, physics-wise. So the phase space is the phase space, right? One might say, my phase space is the plane PQ. I have to explore it all. I never explore it all because it's an infinite space, right? So a question that was always bugging my mind was, how come statistical mechanics wants me to explore the phase space and give it for granted, but the phase space is infinite and I will never be able to, if you diffuse a Brownian particle in an infinite plane, will he ever cover it all? No. So how come I can get ergodicity in a physical system? Do you get my question? And this is where you begin to see. So is there anybody in the audience who did not understand the question that I'm just raising? Okay. Here is where you begin to see what it means available phase space. Because you see, the system is not, it is true that this equation doesn't depend on T, but the system has a thermal energy, KT, right? So if I have my thermal oscillation and I put KT here, I know that in the end of the day, the accessible states will be only those, say, around KT, right? The probability that a fluctuation drives me here at 10 KT is very low, right? Now, if my energy, if my curvature is very steep, what happens? That the region of phase space that I have access to at the same energy is larger or smaller?
Smaller.
Smaller. So it takes me less time to explore the relevant phase space. So stated differently, if I were to draw this, we all know that in in vacuum, the phase space trajectories are just ellipses, right, for an harmonic oscillator. However, we are not in vacuum. We have stochastic dynamics. So basically, there's no phase space for Langevin dynamics because there's no momentum. But let's suppose we do the underdamped Langevin dynamics, okay? So this will not be circle, will be something like this. Maybe a beginning looks like a circle, but then, noise messes it up. And eventually, you get like a cloud, right? But this is the region of positions that you can express. And this region of momentum are basically those determined by the equipartition theorem. So typically, 1/2 KT is equal to 1/2 mq dot square. So p square over 2m, the average p square over 2m, which will give you more or less the scale of this square fluctuation, right, in momentum. So this is the available phase space. Now, this part of the phase space is dictated entirely by temperature, right? I cannot extend this part, the volume in the y direction. I need to increase temperature because that's the momentum. While this part of the phase space is determined by the geometry of the trap, by K. So by going to a harder, I'm basically making these ellipses like a pancake. And the volume of configuration space that is accessible at KT gets smaller and smaller. Do you agree? So once again, let's now use this model to see whether we can extrapolate some general concept from the specific model. What is that? These two models have a different value of K, but K is something that is only attached to an harmonic oscillator. If I had something like this and something like this, where this is narrower than this, sorry for my drawing, you got the point, right? Then of course I could not talk in terms of K, but yet there's something quite specific that is expected to remain unchanged. And can you guys tell me what you think it is? So what is the property that is reduced going from here to here, that is also reduced from here to here? In this case, is controlled by K. In this case, it's controlled by who knows the energy landscape, but the essence is the same. What is getting smaller here?
Entropy, maybe.
Entropy. Entropy is the word. And I want to demonstrate that to you. That thermalization is fast because the entropy of my system is small. There's nowhere to go. And since there's no way to go, you get bored very soon. You've been through it all over again very soon. Like you're like a wolf in captivity. You know, wolves have a big territory, right? When they're free. But when they're in a cage, they keep on walking. And after a while, they've exhausted anywhere to go. They get bored, they run mad, right? The territory is so small that they can, they know it by heart within a couple of minutes. And so the same happens to statistical systems. They explore the system very rapidly, and there we go. They covered it all. So can we relate K to entropy? Because if we can build a mapping, and instead of writing K, we write entropy, we have a model for a general understanding of relaxation on a system. You see what I mean? That's how toy model works. Toy models work precisely this way. You build a model that is sufficiently idiotic that you can solve it analytically. After you solve it, you don't stop and look at your results and say, how good am I? You try to understand what's general in what you did with your toy model, and then you try to extrapolate that into generic consideration. That's the risky part. But that's the risk of business of being a physicist, right? So how do we evaluate entropy? Well, I know the partition function is going to be written like U minus TS, right? Now, if I can evaluate the partition function and I can identify U, then I can identify S, right? So I'm going to do this. I get my partition function. My partition function is an integral over dx. Let me not worry about 1 over h bar. And then there's the volume to the, n factorial. This case is 1, right? The standard Boltzmann problem solving factor in the partition function, because if you have one particle, who cares? Okay? So this is e to the minus beta u, and this is, of course, 1/2 k x squared. But I want to be more generic than an harmonic oscillator. So let me say I have a generic potential here, which may be whatever it is. The important thing, it must have one minimum. And let's focus to the case in which he has one minimum only. If he has more, you can do the same, but you have to just repeat the same calculations in several times. Okay. So let's call x naught the minimum of my potential. So this is the generalization phase. Okay. Now, the same argument applies as in the path integral case. When beta is large, only the configurations of u close to the minimum become populated, right? So why don't you expand the potential around x naught with the minimum? Now, clearly, There's no first order because it's a minimum. Okay, then we're almost done. Integral dx e to the negative beta u of x naught negative beta half second derivative x minus x naught square. And then this is an approximation because there might be non-harmonicities here, but I need to go to the fourth order, because if I put the third order, then this guy is no longer defined, right? Because it gets a negative exponent and a positive exponent, and then one of the two explodes, right? So I have to go to fourth order. But if the temperature is low enough, I never get to visit those tails of the distribution, and I don't care. Saddle point approximation. Okay. Okay, so this is e to the negative beta naught. There we go. The energy is already pulled out. Now, whatever comes now is entropy. And as you see, the entropy depends on the second derivative. So I change variable here for simplicity. And I get a nice Gaussian factor. Now, this is e to the minus bux naught. And I want to emphasize this is now a number, right? Because this is integrated over. So it's a Gaussian. I can do that. It's a root. Now, everything goes if, see here, this is a function e to the basically y over 2 sigma squared, where sigma squared, the variance of this Gaussian, is 1 over beta u second naught. Okay? So as you know, when you do the Gaussian integral, you get a normalization. And the normalization grows with the variance. Right? The result of this integral grows with the variance, with the root of the variance. So we expect this to grow like root of sigma times other constants. Right? There are 2 pi's in this case, actually. I can even say what it is. Okay? Now, there we go. I can put here, I can write this in the following form. E to the 1/2, well, to the log of pi to the 1/2. And of course, there are other constants here, but I don't care, because these constants here, the 2 pi, the root of 2 pi, they enter inside the logarithm. The logarithm of the product is the sum of the logarithms. And then all it does is basically normalize the partition function that I don't care. So the only part that I'm really concerned with is this. So this is basically e to the negative bux naught. And then I get 1/2 this. And then I get the logarithm of the second derivative root, because sigma square is the second derivative, right? To the negative 2. And now I'm trying to remember. Yeah. So clearly, if I write this as e to the negative g beta, where g is the Helmholtz free energy, and g is u negative ts, then I basically get that my entropy is k log 1 over second derivative to the 1/2. So I can put this out. So the larger is u dot is the derivative, the smaller is the entropy. And therefore, I thermalize quicker. Okay, cool. You see, even from such a stupid problem, there's so much to understand. And again, guys, physics is not the art of doing calculation exact, because that art has no room. There is not a single exact calculation in physics. Name me one exact calculation in physics, and I will grant you this course without the exam. Challenge. Don't say harmonic oscillator, because there's no physical system that is an harmonic oscillator. Don't say a Klein-Gordon particle, because it's a collection of a harmonic oscillator, because there's no free particle in the world, because if there was, I couldn't detect it. Don't say the hydrogen atom, because you're neglecting a bunch of stuff in the hydrogen atom. Right? And so on and so forth. There's no exact calculations in physics. But there are important calculations. Physics is the art, quote unquote, of finding the right approximation that gives you information about, the system you're looking at. And even such a stupid model tells us something deep about how thermalization occurs. And okay, so I want to conclude this lecture by saying something about the next lecture. So far we understood that this stochastic approach clearly was speaking to thermodynamics and to statistical equilibrium statistical physics, containing more information. For example, it did contain the Boltzmann distribution as a byproduct, right? But now, remember, one of the things that you never, ever can get from statistical mechanics for free are basically the demonstration of the, so at least in my mind, statistical mechanics is only useful. I mean, I'm talking about equilibrium statistical mechanics. It's this beautiful formulation of averages and stuff, right? Boltzmann. But you can do nothing with it if it wasn't because you know thermodynamics, which is a completely different theory in principle, like formulated in terms of heat, work, state functions, and all you learn from thermodynamics. And you use those extremely powerful concepts and you match them against the averages of Boltzmann, and then all of a sudden you have predictive power, right? You have a microscopic formulation of state functions and blah, blah, blah. That's exactly what we did here. We had a partition function, which is an entirely statistical mechanical concept. And then we postulated this to be the free energy of thermodynamics. And only then we could identify entropy. You see? But I have never found a derivation of the principle of statistical mechanics, of thermodynamics within statistical mechanics in a form that was dynamical. Because in statistical mechanics, there is no dynamics in equilibrium dynamics. You use the ergodic assumption precisely not to have to solve Newton's equations. So in the next lecture, we will show that the stochastic approach that we just described naturally breeds the two fundamental laws of, we already saw the zeroth principle, the equilibration, right? The principle zero of thermodynamics is you reach equilibrium. And we saw within the framework of our stochastic model, we demonstrated that yes, the Fokker-Planck equation has a ground state that is the Boltzmann equation. The next step is, let me demonstrate that the Fokker-Planck equation naturally generates the two principles of thermodynamics out. And more precisely, it generates the relationship between heat, work, and change of internal function, and the connection between reversibility and the notion of entropy. So we will derive the first principle of thermodynamics, and then we will show that the concept, you can calculate the entropy exchange between a particle and the environment because of its motion, and connect that to the concept of reversibility, which is something that you have learned from thermodynamics. A reversible process was one in which entropy did not change, remember? But then when you do statistical mechanics, this idea of reversible process really doesn't make sense because you never change the system. It's always in equilibrium. It's always in one configuration. And so it was always confusing to me to make sense of reversibility in a statistical mechanics sense. And we'll see how this framework allows you to bridge that contact, okay? So Thursday. I'll stop here. There's no point to go to 10 minutes unless you have questions, of course. Okay, Federica, I'm speaking to you simply because you are the outsider of the course. Very welcome one. You did take some theory of the ensemble before, right?
Really not, but I'm trying to see something. I did thermodynamics, but not statistical mechanics.
Okay. You will take, when you will take next year course, things will completely make sense to you. You will be very advantaged at that point because it will sound clear. But, you know, these ideas, you know, you might want to read Tuckerman's book. Tuckerman is actually a friend of our department and our group. We know him very well, and he comes and visits very often. So, but never mind. But he has also written a fantastic introductory course to statistical mechanics, to me at least. It's very simple. Is perhaps a little bit too simple for, you know, if you want to do it professionally, so to say. But it's perfect to get started. It will get you started. Okay.
Thank you.
Good. Ragazzi, buon fine giornata. Stavo per dire buon fine settimana di martedì, il che la dice tutta sullo stato di confusione che ho col lockdown. Ma dai, speriamo che ci si possa almeno alla fine del corso vedere in persona. Va bene, ciao.
Grazie,
Arrivederci.
arrivederci.
Arrivederci,
Salve.
grazie.